All right. Hello, everyone. Today I'm talking about teal. I don't know how the color looks like, but it doesn't look like teal to me. That's a mistake. But so, yeah. But today I'm not going to, just like a clarification. I'm not going to talk about anything concrete. This is more of a programming language talk instead of a kind of actual implementation talk. There will be no implementation. I'm just going to share a very simple but hopefully effective idea. So the scope of this talk is that we're thinking about type preserving compilation from a simply typed source language to some kind of typed target language. And the kind of problem, the kind of idea I'm trying to introduce solves the problem that how do I know what the behavior is my compiled target code, and how do I verify that if I have some specification after compilation. So I was a little bit worried that maybe we're full of like implementers here, so people might be scared of these weird symbols, whatever they mean. But I suppose the general ICFP crowd are usually fine with the typing rules of STLCs, and we'll see more of that. So for those who are not familiar, this gamma is the context for variables, and yeah, I don't think I need to explain more. So that's the source language we're considering, and the target language we'll be thinking about instructions for a SCCD abstract machine, which of course needs to be explained a bit more. So the instructions are, we have a very small and simple instruction set for manipulating over a stack machine. We have you can push things, literals on the stack, you can pop thing, you can copy elements from a runtime environment. You can, this is a very primitive one, so you're allowed to push a closure of instructions and code. Instructions and data on the stack. You can do application, return, sequence things, and the values this abstract machine manipulates are constants, and like I said, a closure of some instruction and a list of values. And the name SCCD machine, it's a very old name from a paper by Landing, I think, and it stands for the 4 basic components of the machine. With the C here is the control, which is the rest of instructions I will execute. And the E here is a runtime environment, which this var would copy from. This S is a stack of intermediate computations, and this D is stand for dump. I think the more modern concept is that it's a stack of function call frames, which is a list of this triple that is the saved data from a function. It's data saved when you do a function call. So I'm still going through what is the shape of my abstract machine. So it has a certain operational semantics that you just look at what is the top instruction, and then you perform the corresponding operation. For example, if the instruction is var of x, then I just find x in the environment, I push it on the stack, and I move on. If it's pop, and the stack has the certain shape, I throw away this v here and move on, etc. And a few interesting things happens when you have these closures. So when I push a closure, then I create a closure with this code and the environment, and I move on. And when I do some application of a closure to a value, what I do is I save, the current information, and I push them on the call frame, and then I load the instruction, the environment, and the input on my machine. So that's a very a simple model of execution. But the interesting thing is we are able to type the instructions like we type the source language using the exact same types, and this is the kind of judgment I want to write. So it says that if this judgment holds, then the instruction I transforms a stack from delta to a stack of types delta prime under the runtime environments of types gamma. So the simplest example is probably this one. So what is the type of var x, variable access? Well, it just turns some stack to a stack with something of type A on it. The same goes for application. So if I have a function, I have an input, I get an output there. And the same goes for push closure, which I get a function on the stack. So that's the kind of picture I'm having right now. But like I said, the problem is, given like a very sometimes a complicated instruction sequence, maybe a compiled target code, how do you know its behavior? Well, we can obviously know what is the type of this massive instruction by like verifying the argument, verifying the judgment. And we do this by, kind of a step-by-step like simulation on what is the shape of the stack. So first, I suppose the stack is empty, and then I, fetch variable x here. So now it has some natural number on top, and then I get another natural number by fetching a variable. I multiply them together. I get one net now, and this goes on until we reach the very end, and we can conclude that this guy has type net. But the problem is, in many cases, you might want to verify that your target code is not only well typed, but when it runs, it will execute exactly this kind of computation. And if you're a human, if you're doing like an exam question, then what you do is you just simulate the program. So you kind of produce an abstract trace of what's going on the stack. And this is essentially the same as the typing rule that I just show you. First I get x, then I get two x's, I multiply them together, and all the way down until I reach the final result, and maybe then I compare this to the specification I want. So this very simple idea I want to introduce today is that this process is like fully automatable, and we can just write them as the typing rules. So this is the the more precisely version of the type system, and where I say that now my type judgment does not just describe what is how the type of the stack transits, but what value on the stack becomes. So here the sigma are a list of well-typed terms of the source language, and then typing judgment says that I transform the stack of content sigma to something content sigma prime, and the idea is that my typing judgment would model the computation just like what we did in this example here, much like maybe an abstract interpreter if you want. So now the modified instructions are all quite obvious. So this should be a variable, but I wrote pop here, but when you're popping an item, then this item is gone. That's it. When you're doing some application with two items on there, then you get one item, which is the result of the application. And when you're pushing a closure, that kind of returns E in the context with extended with X of type A, then you're essentially, the computation you want is pushing a lambda abstraction right there. So that's the general idea. And you might discover that we can do much more than just typing the instructions, but we can also type the entire structure of the machine. So we can type the runtime values, which are just based value, close values of the language. And then we can also give judgments for the environment and the stack, saying that when is an environment implements a stack of shape gamma, and when is the stack implements an abstract stack sigma with respect to some kind of well-formed environment. And finally, we can combine all of these to say that we have a kind of well-formedness judgment for all the machine states. For machine states. But what does this? Why do I do this? What does it give me? So first of all, as a standard requirement for these type systems, it gives us type safety that well-typed programs will step, and if a well-typed program steps, the result is still well-typed. So we get so well-typed programs remain well-typed, and it won't go wrong. But the much better thing we get from type safety with this kind of refined type system is something I call a partial correctness. So to realize that, I should introduce a little bit of the prerequisites. First of all, we can treat a well-typed environment as a closing substitution, which means that it takes, if you apply this substitution, you can turn an open term to a closed term. And then the well-typed stacks are defined to have this certain property, such that if I have these values, the judgment says that these values, v1 to vn, implements these abstract terms e1 to en. Then, applying the closing substitution of any one of these values to the environment, the result would be equivalent to the implementing value. And finally, I define that a configuration holds if eventually steps into the instruction is returned. There's a return value on the top, and there's no remaining frames to execute. So with all of these combined, we know that if we have a well-typed program that is closed and requires nothing to start, such that the initial state with the initialized state where everything's empty, this configuration terminates, then we get the final state must be in this form, such that the result state is well formed, and in particular, this stack is well typed, which means that we will have the situation that the stack implements this kind of closed value v. The result v prime implements the closed value v, which implies that, well, they are equivalent in some sense. So to be a bit more to give you more intuition, it means that not only well-typed programs will not go wrong, it will always perform as you specify by the types if they terminate. So that's I think a very nice property. And what if all of my programs terminate? And indeed, in this case, all of the well-typed SCCD programs, I can show that they all halt. And therefore, with these type safety and termination combined, we get a very strong property, which I call the total correctness, such that if a program is well typed, then executing it will not just halt, but produce a value that meets its specification at the type level. So that's the whole idea. That's the idea. You can make your type annotations a bit more specific. It's so specific that it models the kind of expected computation of your code. And eventually you'll get this very strong guarantee that all of your well-typed programs will perform as specified. All right, guess I'm approaching the end, and so make some final remarks. In the submitted abstract, we've considered a slightly more complicated calculus without the code instructions on the stack, and we have like recursors for natural numbers, which is a lot more expressive than the simplified version I introduced here. But this general idea still applies, and we still have the total correctness, and we kind of require this termination thing to be a crucial aspect, which might sound like a limitation to the expressiveness, but I think termination is quite crucial in certain systems. For example, the eBPF language, you require termination for kernel safety because it wants you to inject code into the kernel, and of course this. If you want to extend this to dependent type theory, then termination is kind of required for decidability of type checking. And so the message here isn't really that we should implement this language I introduced in particular, but we could consider this idea and maybe look at some other type theories with maybe polymorphic types, effects, or even some gradings and quantitative type theory on the types. So, yeah, and here's also a link to the extended abstract that I submitted. Thank you.
Yeah, thanks for the talk. Questions?
Yeah. Thank you for the great talk. So what's your connection of your work to symbolic execution?
Yes. So Could you repeat it with?
What's the connection of your work of such type system to symbolic execution?
Yes, I think it's maybe it's the same concept, but so currently we are kind of limited to the definition of equalities. For example, I suppose in symbolic executions you might have some algebraic properties, like you can equate x plus y with y plus x, but or you can do some like more sophisticated simplifications. But so this one doesn't really consider it yet, but I think it could be used as an extension to incorporate both. Yeah.
Thank you.
Hi, I'm Ala Ahmed, Northeastern University. So how exactly do you prove termination for SCCD? In particular, I assume that untyped programs can
Indeed,
be non-terminating.
You're exactly. Well, the magical two words, logical relations.
Okay.
Yes, so I define a logical relation over the well-typed values,
Okay.
and which for base types they're always true, and for function types I have to say that. So I derived this from a by orthogonality standard, but essentially it says that if a closure of a function type is in the halt if for all instruction sequences that halts given some input. No, hold on. Well, I can write this to you afterwards.
Assuming your
yes.
inputs are terminating, your outputs will be terminating.
Yes,
Basically,
yes.
right? So the trick is that the only types you have for SECD
Okay,
are base types and function types?
indeed,
Okay, perfect. Yeah.
Yep.
So basically it effectively models STLC.
exactly,
Okay,
yes.
got it. Thanks.
Thanks. Any other questions? Okay, thanks so much.
Thank you.
Yeah.